Okay, good afternoon again to you, Dr. Moremi, and to all the participants. Confirm if everyone can hear me.
Yes, I can hear you.
Okay, and the participants as well. Can you just raise some thumbs up just to confirm if you the sound is okay from your side? For confirming. Let me check. Thank you so much for the confirmation. Welcome to today's workshop with the Research Capacity Development Unit at the University of Johannesburg. Findings in the engineering and sciences. My name is Koketso Pila, and I am going to be your moderator for today's session. And I would firstly just like to notify you that this session is being recorded, and I have already clicked on the recording button. And as today in this session. And most importantly, please allow me to thank our presenter, Prof. Lutendo Moremi, for her efforts with preparing and giving this presentation. Before I can officially introduce Dr. Moremi to you, please allow me to go over some of rules. If you do have questions during the presentation, please raise your hand if you would like to speak, or alternatively, you can type your question in the chat box. I will to the presenter to address your question. And also, as I mentioned, that the session is being recorded. The presentation slides and the recording will be uploaded on our Moodle community by the end of today. And also, there is a feedback survey that will be there's a feedback survey that will be pasted on the chat. So please, can we request that you take some few minutes to complete useful and how we can improve in the future. And you can also take this opportunity on the feedback survey to suggest some of the topics that you would want us, and we will organize those workshops. Without further ado, I will then introduce our presenter for the day, Dr. Lutendo Moremi, and in the Department of Electrical Technology at the University of Johannesburg, holding a PhD in Electrical and Electronic Engineering. Background in both academia and industry. She brings valuable practical experience from her time as an engineer trainee at Force Educator, teaching core power engineering modules and supervising postgraduate research. As a leader in the field, she serves chair of IEEE Women in Power uh, from 2024 to 2026, and as the UJIEE student president in international conferences and ISI journals with a focus on power systems, renewable energies, and the application of over to our presenter, Dr. Lutendo Moremi. Dr. Lutendo, just to get confirmation from you, would you like to questions at the end for the question and answer?
You keep on breaking. I can't hear you. You keep on breaking. I'm not sure if it's only me or the audience also. You keep on breaking.
Oh my gosh. Can you hear me now?
Yes, can hear you.
Okay. Asking if you prefer to take questions during the presentation as we move, or you would rather take questions at the end of the presentation.
I think it's best at the end. Can you hear me? I'll
Yes, I
take the
can hear.
questions at the end.
Okay, thank you. You may proceed with your presentation, Dr. Moremi.
Okay, let me just share screen. Can you see my screen?
Yes, I can see it.
The audience, can you guys see my screen?
Some thumbs up. They're confirming that they can see the presentation.
Okay, thank you so much, everyone, for taking time to attend. As you had, I'm Dr. Utendo Mremi from DEET. I'll be facilitating this workshop titled Organization and Interpreting the Findings in Natural Science. Can you see my screen?
Yes, we can see your screen.
Okay, the overview of my presentation will be introduction to statistical techniques, the different types of techniques and the application. I'll also touch on the AI techniques, also the different types of AI techniques and the application data. The statistic is a scientific discipline concerned with collection, organizing, analysis, and interpretation of the data. Before you use this analysis, you need to follow the steps. Step number one, you need to define the problem that you are going to solve. It's either by formulating the hypothesis or identify the population sample or determining the variables that you are going to use. It's either independent and dependent variables. Then you need to collect data and clean that data. Cleaning, we mean removing the errors, outliers, and handling the missing data. Then you can analyze the data using descriptive or inferential statistics. We have two types of statistics techniques that you can use. It's either you can use the descriptive or the inferential statistics. The descriptive one, it focuses on summarizing and describing the main feature based on the calculating the average, the median, the standard deviation. This technique, it uses graphs or text to represent the result. Then we have the inferential statistics. It uses sample the data that you collected to make a conclusion or to make prediction about larger population. Then after you analyze your data, you need to interpret and be able to report that. In reporting, it's either you write a conference paper, journal, or you can write a thesis, a technical reporting. We have different types of cleaning data method. You can use the graphical method. Under graphical method, we have the histograms. You can use the QQ plots. You can use the PP plots or probability plots. Then you can also use the statistical test techniques. In this case, we have many techniques, but I will discuss the Will tests, the Smirnov test, the Darling-Anderson, D-Agustin, and JBP value. All these techniques, you apply them, you calculate the statistics and compare it with the p-values that you compare with the p-value on or the significance value on the distribution table. On the graphical method, we have QQ plots. Just want to get the pointer. This technique, it uses a 5-number summary and a box plot to assess the normality tests. we use it to identify the distribution of the data. Here we are trying to get the outliers before you train your data on the method that you want to use. So this is for cleaning the data. You determine the outliers. So this 5 summary, it divides quarter in 4. You see it's 25, 25, 25. A data point is considered an outlier if it falls at this range or at this range. Can you see my laser? Can someone indicate if they can see my laser?
Yes, we can.
Okay, so it divides your data into 4 quarters. Then the data it's considered to be normally distributed if it's within this 25. If it's out of, we considered it as an outlier, and if it's after the Q3 plus 1.5, it's going to be an outlier. So in this case, we calculate the mean, the median, the maximum, the standard deviation. You can use MATLAB, Excel. Also, you can use the AI techniques. Then from there, you visualize your data by presenting them in the box plot. We did some work on my PhD work, the reference. We analyzed the statistical analysis of low voltage varistor clamping voltage under switching surge. It was published this year. You can go and refer to this paper, but I'll discuss a bit what was done there. We were trying to find the outliers using this QK plot. So we calculated the mean, the maximum, the median, and standard deviation. In this case, in this problem, we had 4 different types of faults, or we have 4 different types of number of surges being applied in this electrical equipment. We wanted to see if the switching surges have the impact on the low varistor voltage. So here we calculated Q1, Q2 for each case. This are the number of surges. So these are different types of group that we apply. So we applied the first group, we applied 4.3 million surges, and so on until we go to the 4th group. So we degrade these MOVs at the same number of surges, 30 samples, then you change the operating condition. Then after that, we use the QK plot to identify the outliers. If you can see from the box plot result, all the MOVs that we degraded, they fall within the standard deviation. So we didn't have an outliers. In a case where you have an outlier, you need to go back and do another test in a different sample. Then you can come again and train it. Then we have another technique that you can use to test the normality test of your data. Remember, this is before you apply your linear regression. This is before you apply any prediction method. This is the other technique, the Darling-Anderson technique. This test, we use the hypothesis based on p-values. So we compare the calculated AD normality with the p-values. The p-values, I believe most of you know if you have done masters. These values is the confidence level value that we have a distribution table that is populated. It's a standard one. So you compare the values that you calculate yourself with the distribution values. So it uses the hypothesis. It tests if the samples are from the normally distributed or not. So this is depend on the p-value. If we have a p-value that is larger than the significant value of 0.05%, it means that they're from normal distributed population. If the p is less than 0.05, the significance level 0.05, it means that we are conducting this research at a confidence level of 95%. So this is 5%, but this is the remaining 5%. So here we are saying that there's no chance that we are conducting this test at 95% confidence level, meaning that we are sure. We are saying at the 95%, this data is from the normal or not normal distribution. So here we calculate the AD, which is an statistics. We use these formulas. Then after that, we plug them in this p-value. Remember, we calculate the p-value to compare it with the significance value. So this is the equation. Equation number 3, it's what we use to calculate the p-values. This is some work where we use these statistics. We were testing the effect of electrothermal degradation in the capacitance of metal oxide varistors. The paper was published in CatCon in India. So what we did there, we had 4 different types of faults or 4 different type operating condition. Then we test all. Let's say we have at 135, we had 30 samples. We calculated the AD squared, then you calculate the p-value. Now you assess if the p-value is greater than the significance value. So in all condition here, for condition, you can see the p-value was greater than 0.05. It means that these samples that we tested in the lab, they were from the same normal distribution test. You can also use the graphical presentation. The graphical presentation, you can clearly see. If you see here, these samples, it went out a little bit, but it was within the range. So it was allowed to use the sample on this data. You can also go to this website. This website, it has the online calculator. All the techniques that you want to use for normality test. If you click this calculator, it will be able to do it for you. But remember, plugging data and getting result doesn't help you. You need to understand why you are applying these techniques. What is the difference from other techniques that you can apply? So this calculator, it has all the techniques that you can use to identify the normality test. Then we have another one, which is the Shapiro will test. This one, we calculate the W statistics. When we calculate the W statistics, then again, we compare it with the p-values from the distribution table. So in this case, again, we use it. It was a different paper. We were using we were identifying the impact of slow front over voltages or number of stages on this capacitance. So we had 4 groups. Again, we calculated, remember this test, you apply it in each group. You don't put all the number of samples that you tested. Let's say in this case, I tested 80 samples, but it was 4 different conditions. So you apply this test in each and every condition. You don't use it as a blanket method to say, I'm putting the 80 samples, then I'm testing the normality. No, you need to test based on the condition. The other 2, it's JQ p-values and Organising. This also compare the p-values on the distribution with the values that you are going to calculate. If you want to know more about this, you can get the paper from IEEE. Then you can also read a journal on the Organising. Organising person, it's a very long technique. So it calculates so many features before you go calculate the D value. If you want to know more, you can go and read this journal. It's there. And if you don't understand something, then you email me or contact me. I can explain more. So what I can say in this technique that we use to test the normality of the test, we compare all of them to the p-values. If their values is greater than p, we can say, and it also depends on the distribution table. We have different p-values. You can have 0.01, which is 10%, 0.05, 5%. It has different significance values. So you must understand why you are choosing a 5% or 10%, or depending on the data that you have. You don't just use any value that you want. So depending on the data that you have, you need to make sure you choose the right p-value. But in engineering, or most of the time we use 0.05. If you check, most of the time we use the p-value of 0.05, which is the 95% confidentiality. Then the advantages of statistical over graphical method. The statistics method, they provide objective numerical assessment of normality. It is sensitive to deviation, so it detects if your value is deviating or to the skewness or the kurtosis. So it depends. When you have the graphical method, you need to have more data. So it doesn't work in less data. The statistical one you can use in small data. And the good thing about this, they're automated. So you can get the system online. It's either on Excel, on SPL, or II. You can get this, it's automated. You just have to plug your data there and come up with result. But before you plug your data, please make sure you understand what you are trying to achieve in each time. We also, in statistical, you can use the formal hypothesis testing. It's either the data is normally distributed or not. The null hypothesis, it's HO, which you will say the data is distributed, or the alternative one, the data is not distributed. Then under descriptive techniques, we have techniques that we can use a data point. I said it, you can use the standard deviation, you calculate the standard deviation, you calculate the variance, the range, the interquartile range. This is what I use on the first slide, where I use the QK box plot. Then the inferential statistics techniques. These are data-driven decision, especially where you don't have time to collect data. Let's say you are manufacturing cell phones. You don't test each and every cell phone. We just test the bunch to say, we use this capacitors, we use this resistance. So we can just test 5 and say at the 95% confidence level, we can say these other benches are okay. So you can use smaller data to predict on the larger data of population. We have tools such as hypothesis testing. You have confidence interval. You can have regression analysis. Where do we use these inferential statistic techniques? You can use them in engineering. We use this to test the reliability and to do risk analysis of the components. The business and marketing guys can also use this to understand the behavior and make the data-driven decision. So in this case, they can say, we are selling houses. Let's check based on where we are, the area we are. They can predict if in the next 5 years, the value will go up or down, depending on what is happening. So these business and marketing guys, they also use it. You can also use it on quality control and manufacturing. So in this case, they use the product to check if the product meets the quality standard without testing each and every item. Let's say we're manufacturing the sweets, 1,000 sweets. We can't test all of them. So we just, or tin fish, we can't test all of them if they meet the quality. You just take the bunch, maybe 10 out of 100, and now you can say at this level, we are confident that the whole of the bunch fall under the name, the same distribution. In economics, they also use to model and predict the economy. That's why the people are able to tell us that in 3 months, the rent will react this way, or the interest rate will go up and down. So they use this inferential statistics. In medical and public research, they also use to conduct trials, clinical trials on the samples. Let's say that testing if this medication for high blood is gonna work on people. So they use certain number of people, they give them that drug, and they check the treatment, the effective of that treatment in those people. So this works at a widely range. It doesn't work in engineering only. Then the inferential techniques, we have the hypothesis testing, we have the ANOVA, we have the regression analysis, correlation analysis. The hypothesis test, this involves the null hypothesis or the alternate hypothesis. We reject or approve the hypothesis based on the significance and the p-value. The significance, remember, it's the percentage. It's either you're testing this as a confidence of 10%, 12%, 5%. So that's the alpha value, the significance value. Then the p-value, it's what you will calculate. And we also have a p-value that it's from the distribution table, that it's across the board. So somebody sitting in America, somebody sitting in Africa, we use the same distribution table to assess this. So it has the standard values. The hypothesis test, it's based on the p-value. If the p-value is less or equal to the significant level, which is the alpha, we reject the null hypothesis. If the p-value is greater than, we can't reject. So we approve the null hypothesis. On analysis of variance, here we compare the different means between two or more groups to check if the means are different. If you have grade 1 student, grade 10 student, grade 12 student, then you have first year student, we give them a test to check the average, which one are performing best. Then we take the mean of each group and compare. So the analysis of variance, we analyze the different means between the group. We check if we can say it's significant, the difference is significant and statistically so. You don't just do. So we also have regression analysis technique. This technique we use to identify the relationship between one or two dependent and dependent variables. We have different types of regression. We have simple linear regression. The simple one, it's when we have one dependent and one independent variable. The multiple regression, we have the more dependent variables. We can say, now we are going to use this drug to check if it has an effect in high blood people. We give them this drug. We also check other diseases and see if this drug is now affecting high blood, or it's now affecting sugar level, or it's heart rate. So the multiple, we check one dependent variable, but on different dependent variables. Then we have the correlation analysis. The correlation analysis, we determine the strength and the direction of the relationship between the variables, between one or more variables. The example of hypothesis techniques and ANOVA, this test ANOVA, we can use it to examine the difference between the simple mean significance, meaning that you are testing all this on the significance level. between two or more groups. So this test, it assesses if the independent variable have the impact on the dependent variable. The following hypothesis, so we use the hypothesis. In this project that we did, we were trying to check if there's a mean difference between the samples that were degraded at 12 hours, at 24 hours, 36 and 48. So these are 4 different groups. We are calculating the mean. So we say these are from the same if the mean of each group are equal. If they're not equal, then we can, this is the alternate hypothesis, but we can reject the null hypothesis saying that the mean is the same if we calculate the F critical value. So we compare the calculated F value. Remember, this is ANOVA F distribution test. So the F here, it's just indicating the F distribution test. So you compare it with the F critical. The F critical, again, we have a standard table for F critical values. So depending on the degrees of freedom on your data, how many data points you have, how many groups you have, you need to check the F critical value. So the F critical value is not always the same. It depends on the data point that you have, the degree of freedom, how many groups you have. However, you can reject the null hypothesis if the calculated F value is greater than the critical value. So if the F value that you calculated using the data that you are assessing, it's greater than the one on the distribution table, then you can reject the null hypothesis. The example that we did to apply these techniques, it was published in this conference. So what we did there, we applied the ANOVA to assess if there's an impact or the changes that happen in the capacitance were resulted from the number of applied surges. So this is the summary table. It's a standard table for the ANOVA. The first thing, you need to calculate the sum of square among the group, within the group. From there, this is the degree of the freedom. You check, it's B minus 1, N minus B, N minus 1. Your B is a simple number. If I use 80, it's going to be 80 minus 1. It's going to be 79. If you use 120 samples, so your B, here, your B value change how your MS and MSW, and also the F critical, and also it will be able to make you choose the right value on the distribution table. So this is how we calculate the F ratio, F distribution, ANOVA. This is how we calculate. So you calculate this, then you can calculate the F distribution, the SA, the sum of squares among, you use this equation. Again, depending on the data, but this just indicates that the SSA is the group sum of squares, where C, it's the number of groups, depending on if you have 3 groups or 4 groups. Remember, the ANOVA, you can only use it when you have more than 2 groups. Then you can calculate the sum within. Then after that, you calculate the mean square among the group, the mean square within the group. Then from there, these values, you calculate your F value. Then you go to your distribution value, you check. It's the F, the calculated F greater than the critical value, the one that you are going to choose on the distribution table. If it's a yes, so it means that we reject the null hypothesis. So the mean are not the same. Remember, the main aim here is to assess the difference between the mean in each group. This is what we calculated. How to analyze it? You can check. We have 4 groups. Then we check the averages, which is the mean. For group 1, we got 1,901. For group 4, we get 1,687. You can see from your eyes that the mean are not the same. The variants are also not the same in each group. So in this case, before we even check the F ratio and the F critical, we can reject the null hypothesis to say this analysis here, the mean is different from these values. Then if you see, to make sure that you are rejecting the null hypothesis, now you must go to your F distribution test, F distribution table, you check. At a degree of freedom where we remember we have 4 groups, so it's B minus 1, 4 minus 1 is going to be 3, that's why you see 3 here. Then we have 80 minus 4, it's going to be 76. Then A minus 1 here, it's going to be 80 minus 1, we have 79 groups. So this will also depend on the number of samples that you are testing for you to go and check this F value on the distribution table. I will show you the distribution table at the end of the class or the presentation. So in this case, it can be seen that the F calculated resulting from this data we use, it's greater than the critical value from the table. So we can say, based on this result, we can reject the null hypothesis. It means that the means are not the same. So the number of applied switching surges, they had an impact on the change of the capacitance of that component when they are subjected to different number of surges. It's not good. Can you hear me?
Yes, Dr. Morin, we can still hear you.
DJ laptop stuck. I think the laptop is stuck. Let me.
Okay, I know we'll give you a few minutes to just set the laptop out.
See, I think, yeah, it's back. Yeah, there we are done using the hypothesis. Guys, there are so many techniques under hypothesis that you can use. So depending on the data, you need to do research. That's why we call it postgrad. There are so many techniques out there that you can use. You just have to check which data do I have, what am I trying to identify, what solution is needed to this data. There are many techniques. So under regression techniques, remember we identify the relationship between 2 or more variables. We also have different types of regression. You have the linear regression where you have one independent, one dependent variables. You have multiple regression. I made an example where we're giving these people a medication for high blood, but we also check on the same person if it's affecting their blood sugar level, if it's affecting that they're having headache, or if it's affecting any other condition that a person can have. We have polynomial regression. This is when we don't have the linear relationship. You can apply it when there's no linear relationship. We have regression trees. This is a tree-based method that uses a series of splits to make prediction. We also have lasso regression. This technique will regulate the important to select future. So depending on the problem, remember the first step to solve the problem here is to identify the problem and see what solution do I need to bring before you can choose the statistics. The simple linear regression, simple, I told you we have one dependent, one independent. We identified this relationship based on the regression coefficient. The equation to explain the relationship when using simple linear regression, we have the coefficient, the slope, and the intercept. Then this is the error term. In linear regression or in regression, we say, we assume that this test must follow the same distribution test. Hence, I started by explaining the techniques that we use to test the normality distribution. So these techniques, the prediction techniques, you can't use your data before you assess if they're from the same distribution. It's gonna affect your result. So before you do any other regression technique, you need to make sure you test the normality. So that's why here we can say we are taking out the error term, reason being we are sure that you tested and you proved that your data is from the same distribution. Then equation 12 and 13, this is what we use to calculate the slope and the intercept on your regression equation. After you train your data, you need to now evaluate. Let's say you predict the model, you find the equation. You can't say that your equation is right or your prediction is right. You need to do some further work to evaluate the matrices of your model. So there are different techniques that you can use. It's either you use a mean square error. This is the equation. You can use the mean absolute error. You can use the root square mean. You can use the coefficient of determination, which is the R squared. You can use the hypothesis test, which is the T test. Here at the T test, you calculate the value of T. Then you compare it with the T distribution table. We already talked about the p-values. We already talked about the F distribution table. We also have another table, which is the t-test distribution table. So these values are standard values. You calculate yours, then you compare it with the standard value. You can also apply ANOVA on the regression to test if your model is fit or not. You can also assess this based on the residual plot. Here you draw the residual plot on your data. We say the model is fit only if the data is scattered around 0 and it has a random pattern. So if you draw your residual plot, you don't see a random pattern, you see the other value, it's at 5 or 10, the other one is at 15. So it means that your model is not fit. So you can't apply that model. In reference 5, we did some work there. We were testing the relationship or the impact of number of surges on the MOV. The MOV, it's a component that we use. It's either in your phone, it's either in your fridge. It's used to clamp the over voltages that can happen instead of switching surges or lightning surge. So this is the important component that you use in your system for protection. It clamps the over voltages down to ground. So in this case, we're trying to see the number of switching surges, how the number of switching surges impact those MOVs. Why we chose to do this work is because we conduct this on the low voltages varistors. The 220 high voltage, the maximum voltage was 220. Why we chose this is because of we're having a problem of load shedding in South Africa. So they were switching on and off. We're trying to find out how these components are affected when they switch on and off. Reason being, the insurance companies were saying the claims for appliances that are going high since load shedding started. So we're trying to identify what number of surges does that affect the MOVs. The MOVs, you can buy them in 10 Rand, but your fridge is 15,000. So we analyze the smaller component that we can replace anytime. Instead of you replacing the fridge, we can replace the MOV. So we will identify the equation to check after how long do we have to replace this MOV. So we predicted the model. We had for 3 different manufacturers, same specification. So we're using different. The other one was manufactured in China. The other one was from the Schneider. The other one from ABB. So we use this to see if we can apply this model in different types of manufacturers, even if it's the same specification component. So we use those equations to identify your slope and your intercept. So in all 3 manufacturers, we got the same trend, which we had the minor slope. And from this, we could see that for each and every number of surge that is being applied, this component is been affected. For manufacturer 8, it was 0.02. For manufacturer B or Y, it was 0.05 and 0.03. So for each and every surge that we were applying in that component, it was changing by this value. But if you can see, the trend is the same. The manufacturers are different, but the trend is the same. So we use the t-test now to assess if our model that we predicted, it's fit. Can we say, is this model okay? Or were we not supposed to use this to determine the relationship? Remember, I told you can use the mean square error, you can use the R squared, you can use the t-test. So in this work, we use the t-test. The t-test, we calculated the t-test in each case or in each manufacturer. Then we check the T critical value. Remember here, the T critical value is 3.81 across because of we had same number of samples in each manufacturer. So the T, it's getting affected, or the number of degree freedom. So this doesn't change as long as your number is the same, number of samples is the same, then the critical value is the same. But you see the t-stat or the t-value calculated, it was not the same, but they were all greater than the critical value. So we can say at the level of 95% again to say, no, the model that we trained using was fit for this data. So we can take this model out there. And the p-values, in this case, when you do the p-values, the significance value must be greater than. Remember when we applied the normality test, they were supposed to be greater than 0.05. On the T-critical, now, the calculated one, they must all be less than the significance value, 95% confidence, which relates to 0.05%. So we can say that because of these values, all the values for these models, they were less than 0.05. So we can say this model is fine. Please don't mix with the normality test. The normality test, all the p-values, the calculated values must be greater than the significance value. For the T critical, they must be less than 0.05. These are the results. Remember, we use different manufacturers, manufacturer A, B, C. So this is what we found. The multiple R, the R squared. Before you even apply the t-test, you can see that checking the R values, the multiple R values to get 0.98, this means that this result didn't happen. by chance at 98%, 98.5. So before you even go to test your model, you need to check, to analyze your data, to know these terms, to see which one do I check. In this case, I check the R squared. The R squared here, they are over 0.9, which is like 97%, 94%, 92%. So this model was good for all manufacturers. Then you can graphically show your model. Excel can do this for you. MATLAB can do. So it depends on the tool that you are using. You are going to get the same model. This is the residual plot. Remember we said if you don't want to do the t-test, you can also assess if your model is fit based on the residual plot. So the mass be scattered between 0. You see here it's 1.2, 0 minus 0.8. You can see it's not far from each other, and we have a random pattern, so we can say thumb up, the model works. We can also use another technique, which is the Kruskal-Wallis test. This is an alternate way to ANOVA, one-way ANOVA. Remember the ANOVA, you assess the mean between each group. You must have more than 2 groups. So in this work here, you first need to rank all the calculate average grain sizes, or whatever the averages that you are using on your data, or on your data that you are trying to analyze. So here you are going to calculate all the average of people that, let's say the age, you are giving this drug to people who are 36 years, people who are 76 years, people who are 100 years. So you need to first calculate the average. Let's say you have 30 people who are 30 years, 30, 90, 30, 100, then you calculate the average. From there, you find the total rank in each group. Then you can determine the age test. In this case, the age test, remember the ANOVA, we check the F distribution value or the F critical value on the distribution table. In this method, now we compare it with the chi-square value. Again, the chi-square values, we do have the distribution table. You just go to internet and check the chi-square value. So if the one that you calculated, it's greater or equal to the chi-square value, so it means that there's no impact or there's no difference. If it's, let's say the chi-square value is 2, you calculate your age statistics at 4, it's going to be greater than chi-square. So we can simply say that this drug, it has an impact in the behavior of these people after they take this drug. Then how to perform these statistics? You can use machine learning AI techniques. You can use MATLAB, you can use Excel, you can use SPSS, depending on which tool you have. So you can use this. You can apply the Darling-Anderson test on the AI. You can do the modeling. So it's not limited to say we're going to use it. It's a statistical, however, you can apply it on machine learning. So you can use your Python to calculate these K values, these P values, these AD values, depending on the tool that you have. You are probably going to get the same answers. Then the machine learning techniques, are they different from the statistical method? Yes, they are different, even if they often overlap or use similar mathematical. I just said now that you can calculate the AD test, the Darling-Anderson statistics using machine learning, but it's different from the machine learning techniques. The machine learning techniques, they are computer-based, and their primary goal, now we check the accuracy, and it requires more data. With the statistical techniques, you can plug your 20 sample data, you can get good result. But in machine learning, you need to use more data. And also machine learning, we use it to predict the accuracy or to classify. So the statistical approach, it will involve a formal hypothesis. You must use different regression model depending on what you are trying to find out. Let's say I'm trying to check if the student attendance in class affect their pass rate. With the statistical, I'm just going to use the number of hours we attend or the number of classes that they attended based on and compare them with the pass rate. But in machine learning, you require more features. You need to check things like hours, the studies, how the online activities, if they were logging in on Ulink or if they were using the material that you upload on Ulink, how do they use them? Do they download them, or someone just take their phone, they browse through, they are sleeping, then they don't download? In machine learning, you need more features to train, but in statistical approach, you can use less data. Then the machine learning techniques, we have supervised and supervised classification method. The supervised one, the model is trained with the label data, so we already know the answer. The aim of using the supervised is to learn the relationship between the output and the input. Then the unsupervised machine learning, the model is trained on the unlabeled data, and we can use them for classification, for prediction, for clustering, for also if we know the fault, we want to try and find the fault based on the number of surges we can predict to say in the 20 years this MOV being online, it's going to fail or it's going to be still alive, so we can predict the lifespan of a component in engineering. So we have different type of classification. Remember, classification, you are just trying to classify. We have different type of classification, logistic regression, we have decision trees, we have random forest, support vector machine, the KNN, the gradient boosting. It will depend on what are you trying to achieve based on the data that you have. Which one can be best? So they are there, techniques are there. You just have to study your data and see what you are trying to find. And now you can use the technique that can help you. So the logistics ones, it predict the chance of something being in one group. The decision trees, it use the equations and answers in a tree shape. The random forest, we use different types of trees working together to make a decision. The support vector machine, they separate the data into group by dividing it with the line or the boundary. The KNN, this we find the nearest neighbor, which point it's next to each other. Then the gradient boosting, this build many small trees, then you can be able to classify your work. Let's say, for example, I am going to classify if in a class we have boys and girls. How many boys and girls do we have? We will use the data, the number of classes, the classification method will be able now to tell us this based on the age or based on the on the behavior of this student. This student, we can classify him as a boy or as a girl. So it must have many features. This is the example that we did in one of the work. We used the KNN to classify the degradation condition of these MOVs. Guys, if you see from the beginning, I'm talking about MOVs. It's my special point. It's where I specialize. So we're degrading this MOVs in different conditions. Then we fit this data based on the output. We assess if the KNN can now classify to say, was this MOV degraded at 1,000 surges or million surge, 10 million surge, or more surges. So we had different types of operating condition. We feed the data and the output. The output in this case, we're using the clamping voltage. So we before we degrade this MOVs, we measured the clamping voltage. After we measured, and for each operating condition. So we group them. We use the supervised because of it had the labels. So we have different types of conditions. We labeled them. So we fit the data. We check if it was able to classify the degradation condition. So in this case, we use this formula, the closer-than distance. You check the distance between those data points, and after that, it will classify. It will classify each data point. The KNN, we use the accuracy to check the metristics. We also check the precision call. We also check the F-score. And now we calculate the total accuracy. So the total accuracy and the F-score must not have much different. If it has a wider difference, it might mean that your data is not fit for this model, or you tried and manipulated your data, which we see most on our postgraduate student. They come with good result, but they can't explain them. When you ask them why your F-score, it's like 60%, but your accuracy is 99, then they start looking down. And so you need to check the things. You need to read to understand what's the difference between the accuracy and the F1 score. How does one affect each other? So you must make sure you understand these terms. Then we remember we had 40 samples in each different condition, under 60 degree, under 85, under 110, and under 135. This represents the number of stages that we put. If you check the F1 score, 70, 82, 75, 74, then we calculated the overall accuracy. It gave us 96.3. So if you check the F-score between these groups, they were more or less related. And remember, on the machine learning, you need to divide your data. It doesn't mean that I had 40 data here, 40, 40, 40. I'm going to train the whole 40. So I divided into 80% for training and 20% was for testing. So this KNN, if you can see here at 60, it classifies that the 30 samples out of 40, the 30 samples here, they were classified correctly. Then it misclassified other at the 2 at 85, this at 110, 3 at 110, 2 at 110. At the 85 degrees Celsius, out of 40 samples, the 34 were classified correctly, and the other 246 were misclassified. So it had other two that were misclassified at 85, the other two was at 110, the other two were at 135. But remember, using the statistical techniques, even if this was classified, you will find out that on the statistical techniques, it was within the range. So you might find out here the maximum was 7.5, but we have 7.6, 7.7. So this KNN will misclassify that, will take it to the next level. So that's the good thing about machine learning. It can detect the smallest deviation. I think that's the end of my presentation. Thank you.
Thank you so much, Dr. Moremi, for that detailed presentation. I will now open the floor for questions, and I'll just allow everyone's mic so that those who would want to, ask questions can just unmute and then speak from their side. Just a few minutes, just 2 minutes, while I try to change the settings to allow everyone to speak. Okay. So let's make use of this opportunity to engage with Dr. Moremi so that we can learn as much as possible from this workshop, and to get our questions answered so that when we leave the workshop, then all the confusion that we had can just be addressed. So I see we already have a hand from Vincent. You may unmute yourself, Vincent, and ask your question.
Hi. Firstly, thank you, Dr. Moremi, for giving us this whole picture. Is it possible then to get a presentation from you posted to us?
Is it possible? What? I didn't hear you.
For us to get your presentation.
I'll share it with the guys. They will share it with the attendees.
Thank you. Thank you, Mr.
I think there's also more in machine learning. If you checked, I just discussed the classification. I didn't discuss the prediction, and because time is limited. So if possible, we can have another session where now we are going to discuss the machine learning prediction techniques, like the way we did with the linear regression. We can also use machine learning on that. So I believe it's another session for another day.
Okay, Dr. Moremi, well, we are open for that. So if the participants would like another session, then you can just let us know the date that suits you, and then we will arrange that workshop. And we have another question from another hand, rather, from Nontlantla. Nontlantla, you may go ahead and unmute yourself and speak.
Thank you very much, Prof. and colleagues. Good afternoon. I think it's a very useful presentation, even though one is struggling a little bit around some of the areas. I'm requesting that she explain again the decision tree, such that I fully understand whether I've grasped what she's making a reference to. I think part of what I'm battling with is how to deal with the analysis in terms of the data that I've already collected. And as she was explaining some of the areas, I think it did click on the decision tree, but whether I'm concluding the right way, if she can explain, maybe re-explain it again, I will be able to help myself. Thanks.
Okay, no problem. On the decision tree, I just mentioned that we use questions and answers in a tree shape to make the decision. So if depending on the data that you have or the question, it will help if I can see what you're trying to find and what we can conclude. Maybe you can email me if you don't mind. I'm not taking a supervisor space. I will just be trying to help. So I need to first read what data you have, what you're trying to get, then we can come up with conclusion. I'm open for that. Because remember
Thank you very much. I think you went into the direction of what I was praying you could say. Thank you. I will email.
Yeah, just email me, then we see. Because we need to identify first. Remember, we can just say it's a decision tree. We are using different trees. But what is the core question for that research? It's not going to have the same conclusion. So it's better to try and see what we are trying to find and what conclusion we can make.
Thank
So
you. I'm gonna drop my email. I'll drop my email on the chat, and you can probably respond back so that I'm able to answer.
Just my email, it's elmoremi@uj.ac.za, so you can drop me email straight.
Thank you. I didn't get that. Thanks a lot. Right away, I'm on it.
Okay.
Thank you, Dr. Mremi. I see that a lot of the postgraduate students are actually happy with the suggestion to have a follow-up workshop. I see some comments on the chat box that they will be happy for that follow-up workshop. And so we will then hear from you with the date that you're most comfortable with, and then we will make those arrangements for the workshop. And there is also a comment from Moloko who says classification can also be done in a predictive way. It is not prediction versus classification. Yes.
Yes, you can do it in a predictive way. Hence, I said I think it's better to have a session based on the machine learning. If you see, I base too much on the statistical techniques. So it's if we can have more example and see where we can apply it on the incoming session. Thank you for that.
Definitely, thank you. I don't see any other hands or comments on the section box. I'll just encourage those who still have, questions to just bring them up, so that we can have a discussion. We still have a bit of time in this workshop, so let's make use of this opportunity to just engage with Dr. Moremi, and just also to remind you that there is a feedback survey on the chat. Please, can you take a few minutes before you leave the workshop to complete the survey so that you can give us some insights on how you found the workshops and how we can also improve in the future. Thank you for the comments. Also, Molok is saying great presentation, well done. Thank you for that. No more questions. I'll just give a last round of questions for those who would like to raise their questions. This is an opportunity to do so. I know this is a Friday afternoon, but let's get those questions answered. Okay, let me see the
Honor
chat.
student, electrical engineering, DFC. Why are you guys quiet? Are you okay?
This
We
means
are
that
having feedback 5 soon. And you
Yes.
need to present your result. So it's best to ask.
Well, I see the comments are very positive and they're saying the presentation was great. So it means it was very clear for them to understand, and follow. So we truly appreciate that. And, if there are no more questions and, comments and some hands that are raised, then we will go ahead and close the session. Just before I do that, I'll just like to express my appreciation to Dr. Moremi for availing yourself today to facilitate this session. We truly appreciate your insights. It was very detailed, and as you have said, that a follow-up session will be good. So we are open for that, as well as I have mentioned, and that we truly welcome the suggestion for for a follow-up workshop that will benefit everyone. So thank you so much for this workshop. It was insightful, it was detailed, and we took a lot from the session. And also just to thank the attendees for taking the time on this Friday afternoon to attend the workshop and engage. I mean, these workshops will not be as engaging if you do not attend. So your presence, your attendance means a lot to us, and it shows that the workshops that we're organizing, they are appreciated. So we truly thank you for taking the time to join us today. And if there are no more questions, I'll just give Dr. Moremi to make the final remarks, and then we will end the session. Any final remarks, Dr. Moremi?
I believe, my office, you can come anytime to each case is different based on your data and what you're trying to find. So I'm available to help. You can email me. Thank you so much.
Thank you. Just to also reiterate that we will share the presentation slides and the recording as well to those who attended. So thank you very much, Dr. Muremi, and thank you to everyone. Let's have a great day further. Thank you.
Thank you. Bye.
Bye.
Bye, Dr. Murray.
Thank you. Bye.